Hello, how are we doing today? In this video, I'm going to start out by talking about the composition of functions as it pertains to continuity. In particular, to make a long story short, the composition of continuous functions is continuous, assuming that all domains are appropriate. So if F has a domain D, and let's just assume D is not empty, of course, and G has as its domain the image set F of D. So we're going to let F of D be the image set of F. In other words, F of D is a collection of all elements that D gets mapped to under F. Okay, then the composition function G compose F will have D as its domain. Well, sure, but that's not very exciting. If, in addition, F is continuous at x equals c, while G is also continuous at f of c, we're assuming all this, then it will be the case that G compose F is continuous at x equals c. In other words, the limit as y goes to f of c of G of y equals G of f of c, which is G of the limit x goes to c of f of x. So continuity, if F is continuous at c, and if G is continuous at f of c, then G compose F is continuous at c. That's a very nice thing to have. The composition of continuous functions is itself a continuous function. And one thing I need to say during this video is we're going to assume without proof that the limit as x goes to 0 of the sine of x over x equals 1. This one we're going to use. And later on, but not now, we're going to use this one as well. This limit is 0. As such, the function f from r to r such that f of x equals sine x over x for non-zero x, and such that f of 0 equals 1 is going to be continuous at any real number, including 0 itself. So we're going to need that. That's for the next example I'm fixing to do. For example, if f is a function from r to r such that f of x equals 2x for all x for any real x, and if g is a function from r to r such that g of y equals sine y over y for the non-zero reals, while we go ahead and define g of 0 to smoothly equal 1. This is a thing we're going to call the sinc function a little later on, though, but anyway. Then D equals R, because here's my F, my domain of my F is R. But also F of D is R, because in fact, every real gets sent, if f of x equals 2x, F is a bijective function, so I go from the reals onto the reals, bijectively in fact. So we get D equals R, which is F of D. That's nice. Doesn't always happen that way, but in this pretty example it does. And G compose F is going to be a function from R to R. And in fact, it is going to be, well, yeah, it's a function from R to R, and then such that G of f of x, that's G compose F right there, guys. So G of f of x equals, now the sine of 2x over 2x, remember, if I compose functions G of f, instead of G of y, we're doing G of f. That's the sine of f over 2f. But f equals 2x. Or I really should say, instead of f, I should say f of x. But I'm being a little bit lazy. So G of f of x is the sine of f of x over f of x. But remember, what is f of x? It's 2x. So we get sine 2x over 2x. Okay, which is nice. Okay. And, of course, well, I do need to qualify. G of f of 0 would be G of 0 itself, which would be 1. So I got all that typed in. Sorry about that. Sorry for the pause and delay there. So I need to sort of throw that in just to be complete. So let's just say let's just pick some c. Let's say c equals 5. Then let the limit as x goes to c to 5, my c is 5 here, of G of f of x is G of f of 5. I can safely do that because the composition of continuous functions is itself continuous. So I get the sine of 2c over 2c, but c is 5, so that's just the sine of 10 over 10. Okay, so, and that's good. The composition of continuous functions is itself a continuous function. Okay. And here's another example. The limit as x goes to negative 36 of the square root of negative x is going to be the square root of, well, by continuity we can throw negative 36 into x right here, but guys, the negative of negative 36 is pos 36. So the square root of positive 36 is 6. And in a separate example, the limit as x goes to 5 of the cosine of 4x. Remember, we're assuming trig functions are continuous, and we're assuming polynomials are continuous. This is the composition of continuous functions right here, so it's going to be continuous. So we can just throw that 5 right on in there, and we get the cosine of 4 times 5, which is the cosine of 20. And now in this example, it's a bit of a tongue twister. If f is a function from 0 to infinity, or I should say, yeah, that's true. Let's call that the non-negatives. So from the non-negatives to the non-positives, such that f of x equals negative x for all x in the non-negatives. And if g is a function from the non-positives to into the interval 7 comma infinity closed at 7, such that g of y equals the square root of 7 minus y for all non-positive y. Okay, so we're taking the non-positives and we're going to throw them into this subset of positives right here. So this is non-positives. We're throwing them into a subset of the positives. So you're going to go from 0 or else negative to being a positive number. And that's what g is going to do to you. Notice that for this radical to make sense, 7 minus y had better not be negative, because we don't want imaginary or complex numbers. We want take the square root of a positive number here. Okay. Then the domain of g, which is neg infinity to 0, by the way, equals the image set of f. Sure, here it is, right here. Namely, neg infinity to 0. Yep. And so g compose f is going to be a function from the original f domain, 0 infinity, to the image, or to the image set of g. And that is going to be the image set of g. My codomain, sometimes the image set is actually smaller than your, this is called the codomain here. Sometimes your actual image set, what you map down to, is smaller than this set. It's a subset of it, I should say. But in this case, this is actually going to be both. It's going to be my image set as well. So 7 infinity, I can safely say, is my image set. So then the domain of g equals the image set of f. Well, yeah, we already talked about that. And also so g compose of f is going to have an image set of 7 infinity also. And these are both going to be bijective functions. Yeah. So g compose f is going to be bijective. That's true from algebra. And from what we just said, now they're both continuous on their appropriate domains, so their composition is going to be continuous on its appropriate domain, which is the same domain that f has. Okay, so the domain of g equals the image set of f, namely this, and g compose f is going to be a function from the very beginning to the very end, which is the very end is this guy here, such that g of f of x is radical 7 plus x. Now guys, how did I get that 7 plus x in there? Remember, g of f is going to be radical 7 minus f. 7 minus f, but f is negative x, so we're going to have 7 minus a negative x, but minus a negative turns into a plus right here. Okay, this negative x, and 7 minus negative x is 7 plus x. Because that y would turn into a negative x right here, but that makes it plus x right here. Okay. Furthermore, we have the limit x goes to c of g of f of x equals the limit as x goes to c of g of f of x equals g of f of c, which is radical 7 plus c. When I say radical, I mean square root, okay? And so that's just an example illustrating all this. Thank you guys. We'll move on to the next video.